Let's solve section B from the 2022 Intermediate Physics Challenge. Before we get started, just a little note that these are not official solutions and you should go ahead and check out the British Physics Olympiad's website because it's awesome. Okay, well, let's have a look at question 11. By the way, if you're looking for the multiple choice questions, they are in a separate video. So what do we have in this short answer question for 5 marks? So in 2022, there were 2 solar eclipses and 2 lunar eclipses. What we need to explain is why a solar eclipse can be observed directly from only a relatively small area, whereas a lunar eclipse can be observed directly from many different places on Earth, covering a much larger area. And we should draw a diagram. Well, here's my little diagram for this. First of all, we can see that when we have a solar eclipse, this happens when the moon is between the sun and the earth. Now, the moon is smaller than the earth in comparison, but it's also quite close to it, meaning that the shadow region is very small. So we're only going to observe the eclipse if we are around this region. On the other hand, when we have a lunar eclipse, now this occurs when the Earth is between the sun and the moon. And this entire region here is actually within the shadow. And this means, should we just highlight this just to showcase the region through which an eclipse will be observable. So this here is the entire shadow of the Earth. I'm going to just kind of do that in gray, and meaning that if you are on the part of the Earth which is facing the moon at any given time, you will be able to see the lunar eclipse. Obviously the Earth is rotating, so there's going to be some regions that are not going to catch the eclipse initially, but they might be able to given the rotation of the Earth. So hopefully this diagram and explanation will be able to score us full marks. If you look at the website for the British Physics Olympiad with the official mark scheme, there are a couple of extra points that you might want to have a look at as well. Okay, question 12. An ideal voltmeter has an infinite resistance. In reality, voltmeters don't have an infinite resistance, but have a very high resistance. The circuit shows a bulb in series with a power supply and an ammeter, both of which have negligible resistance. Explain why an ideal voltmeter should have infinite resistance. Well, we don't really want it to affect the current, so this is one thing that we can add. So it should not affect the current. The idea here is that if I have some current which is going down here, unless the voltmeter has infinite resistance, the current will split into 2. So let's say we have I total here, then this will turn to I1 and then I2, and then they will kind of join together afterwards again. And if it has an infinite resistance, this will not happen. And the way I'm going to word this is by saying that current should not take the parallel branch of the voltmeter. Okay, next one. So for the circuit shown, state and explain. So we need to do 2 things, state and then explain how using a voltmeter with a resistance of 1 mega ohms instead of an ideal voltmeter would affect A, the current measured in the circuit by the ammeter. It's actually a really interesting question. So if it's just the bulb with no current going through the voltmeter, we're going to get a certain reading. However, if we were to add more things in parallel, this means that we need to draw more current. Therefore, the current through the ammeter will increase because we'll no longer be providing just current for the bulb, but also current for the voltmeter. So what I'm going to say is that the current will increase as more current will be needed for the parallel branch. Okay, B, the potential difference measured across the bulb by the voltmeter. Well, they're in parallel, and therefore the voltmeter reading will not change. So I'm going to say that there will be no change to this. This is the state part of the question, as the bulb and the voltmeter are in parallel. Okay, C, resistance of the bulb calculated using the relationship R is equal to V divided by I. Okay, well, if we are using a voltmeter, then a voltmeter with some resistance, then as we said that the measured current I total will be higher. Now, because the resistance is inversely proportional, if I is high, a little bit higher, this means that R will be a little bit lower. So we can say that R, or the resistance, will be lower. So the resistance of the bulb will be lower as the measured current will be higher, and they're inversely proportional. Okay, extended written questions. So let's have a look at the next section, and let's have a look at question 13. So this question is about a school practical to measure acceleration, where a student investigates the acceleration of a toy car on a ramp. So the height of the ramp is changed, and the resulting acceleration obtained from the measurements are given below. And we have the following experimental setup. We have a toy car that is going down a slope at a length of 1.2 meters. So to measure the acceleration, the student releases the car from rest at the top of the ramp and uses a stopwatch to time how long it takes for the car to reach the bottom. And we have the following recordings. We have the ramp height, the time, with 3 different attempts. Okay, so let's calculate the average speed of the toy car. Okay, so to calculate the average speed of the car, I'm going to need the average time. So to find the average time, all I need to do is find the algebraic average. So in my calculator, I'm going to put 2.45 plus 2.48 plus 2.41. Then I'm going to divide that by 3, and this is equal to 2.449, I think. So up to 3 significant figures, this will just be equal to 2.45 seconds. Okay, this is the average time though. To calculate the average speed, I'm going to need to divide that by the distance traveled. So the average speed, I'm going to call that V, will just be equal to 1.2 divided by this number, which is 2.45, which is equal to 0.49 meters per second. So part B, explain why the teacher's statement is reasonable, stating any assumptions that are necessary. And the assumption is that the final speed of the car is twice the average speed. Well, there's a formula for constant acceleration, and that formula says that the distance traveled, S, is equal to a half U plus V multiplied by T. And this is part of a set of equations known as the Suvat equations that if you do A-level physics, you'll study in great detail. Let me know in a comment if you'd like me to derive this equation, for instance. Okay, anyways, so if we were to rearrange that for S over T, so I'm going to make S over T the subject of the equation. S over T will be equal to a half U plus V. Now, S over T is just speed. So what I'm going to say is that V is, or S over T is the average speed, sorry. v average will be equal to a half u plus v. Now in this case, u is the initial velocity and v is the final velocity. Now our assumption for this problem, there are two assumptions actually. The first one is that u is equal to 0, or the initial velocity is equal to 0. The other one, which they probably don't want you to write, is that this will only work if the acceleration is constant, which in this case it is, because we're talking about gravitation. So if u is equal to 0, then v average simply turns into, v average is equal to a half times the final speed, or the final speed is equal to 2 times v average. Okay, next one, C, calculate the acceleration of the toy car. Well, let's use the formula for acceleration, that a is equal to our change in speed divided by the time. Now for the final speed, I'm going to use twice the average speed, so it's going to be 2 times. What was the number for the average speed? There it is, 0.49. So 2 times 0.49. Take away the initial speed, which is just 0, and then divide that by the average time, which was 2.45. 2.45, and let's put this into a calculator. And that's going to give me right about 0.4 meters per second squared. Okay, then the teacher states that theory suggests that the acceleration of the car is directly proportional to the height of the ramp. Then we take some further readings of time for different heights of the ramp. Use the student's data to show that the acceleration of the car is proportional to the height of the ramp. So this is actually a technique that we use in A-level all the time, and it appears also in this Olympiad. So if something is, I'm going to write this over here on the side, but if something is proportional to something, so let's say that the acceleration is proportional to the height, this means that there's a constant of proportionality, which I'm just going to call k. So a is going to equal to k times h. So this means that a over h will be a constant. So this means that if I take some values of the acceleration, then I divide it by the height, then I am going to get exactly the same number. And this is what we need to do. Okay, so we have the data for our first example. So let's say that when the height is 5 centimeters, and the height was just initially 5 centimeters across here, we have our acceleration, which is 0.4 meters per second squared, and we know our height as well. So this means that for this example, a over h will just be equal to 0.4 divided by the height, which is 5 centimeters. So this will be equal to 0.05. And plugging these into a calculator, we're going to find that a over h is going to equal to 8. Now the units of that, a over h, so what is that going to be? Meters per second squared divided by meters. So that's just 8 seconds to a power of -2. Now let's see whether we can repeat exactly the same calculation for the 9 centimeter mark. So let's switch back to the pen. So for 9 centimeters, we need to find the acceleration. Then we're going to need to divide that by the height. So the acceleration for 9 centimeters will be equal to v take away u divided by t. Now what is the speed, or the final speed? Well, the final speed is equal to twice the average speed. So let me just write this as twice v average, and then the initial speed is u, divide that by t. Okay, well, the to figure out the acceleration, we're going to need the average speed. The average speed, on the other hand, will just be equal to 2 times, or to figure out this expression, I'm going to need to multiply 2 times the average speed, and the average speed is just equal to the distance traveled, which is 1.2 meters. That's just the length of the ramp. And then we're going to be dividing that by the average time. So the average of 1.84, 1.82, and 1.82, and if we put this into a calculator, basically the average for this column is 1.83 seconds. So 1.2 divided by 1.83. Then I'm going to need to divide that by the average time again, which is 1.83. And up to 2 significant figures, this here will give me around 0.72 meters per second squared. So for 9 centimeters, A over H will be equal to 0.72. Then I'm going to divide it by the height, which is now 9 centimeters. So it's going to be 0.09. And this will also be equal to 8 seconds to a power of -2. Now what I'm going to do is I'm going to repeat exactly the same procedure for the 13 centimeter height row. However, what I'm going to do in this formula here, I'm going to now be dividing by the average of those 3. So the average of 1.5, 1.52, and 1.56. Okay, well, the average of this row here, so T average for this height is no longer 1.83, but it's in fact equal to 1.53. So the acceleration will be equal to twice the average speed, so it's going to be twice times 1.2 divided by 1.53 divided by t, which is 1.53. And let's put this expression into a calculator. And up to a few significant figures, we're going to get around 1.03. So the ratio of A divided by the height will be equal to 1.03 divided by 0.13. And this is equal to around 7.92, which is very close to, well within probably experimental error of those 3 values. So we have successfully used the data to show that the acceleration of the car is proportional to the height. Okay, next one, the theory shows that the relationship between h, the acceleration, and the rest is given by A is equal to GH divided by L, where G is the acceleration due to gravity. Use the student's data to calculate a value for the acceleration due to gravity. Okay, now in the previous question we worked out the ratio of A over H, and chances are I will probably need to be using those in this equation. So the first thing I'm going to do is I'm just going to rearrange this for G. So G will be equal to LA divided by H. So what does that mean? That means that if I take L and then the length, which is just 1.2, then multiply that by A over H, then I'm going to get my value for G. Now, I shouldn't really do this for just one result because I have 3 sets of data for AH across here. So I'm going to do this 3 different times. So for 5 centimeters, G will be equal to 1.2 multiplied by A over H, which is 8. For 9 centimeters, G will be equal to 1.2 multiplied by 8, so it'll be exactly the same value. And for 13 centimeters, G will be equal to 1.2 multiplied by 7.92. Okay, well, if we put these into a calculator, what we're going to get is a 1.2 times 8 is going to give me 9.60 meters per second squared. In the first case, exactly the same for the second case, 9.60 meters per second squared. And for the final case, it will be a little bit lower, which will be equal to 9.52 meters per second squared, where the last digit may be a little bit different in your results, maybe perhaps due to rounding. Okay, next one, the student comments the value of G is not very accurate, but we only have measured the ramp to nearest half a centimeter. But the student's teacher disagrees and replies the lack of accuracy due to the random errors in the timing. By considering the range of values of the timing and the uncertainty in the measurement, determine whether the conclusions stated by the student or by the teacher are justified. We have some hints to calculate the uncertainty in a measurement as a percentage of the average value, making it easier to appreciate the significance of the uncertainty. Okay, so we're given a load of different hints in the question. It'll be really useful to do exactly as they say. So our reading on average was around 9.60, so G was 9.60, and our percentage difference, so percentage difference would have been around 10, take away 9.6, which is 0.4, and then which is going to be approximately equal to 4% out of the accepted measurement. Now, the height of the ramp to the nearest 0.5 centimeters. What effect would have that had? Well, the uncertainty of plus or minus 0.5 centimeters gives us a range between 10% of the 5 centimeter reading and around 4% for the 13 centimeter reading. Now, to work out the average in the actual time, what we need to consider is the range of values. So we need to go back to the different times and then work out the actual range. For instance, the range on this one will be equal to 2.45, which is the highest reading, take away the lowest reading, which is 2.41, which is around 0.04. Then I'm going to divide that by the average value. So that will be 0.04 divided by 2.45, multiply that by 100 as a percent, and up to one significant figure, that's around 2%. I can repeat this for the other two sets of readings. So repeat exactly the same process for this one and for this one. I won't bore you with the calculations for this, but what we're going to find is that the range of the timings was so it was 4%, sorry, it was 2% for the first set of reading, and it was actually 2% for the second set of reading, but only 0.5% for the larger height, and for the third set as the reading was just larger. So in reality, what's actually caused this difference of 4% is the combination of both of those effects. So what I'm going to say here is that both the timing and the height measurement will have affected the uncertainty. Okay guys, we have one more question left. However, I'll be posting this in a separate video because otherwise this video is going to become way too long. Now, if you're looking meanwhile for the multiple choice questions, have a click right over here, and thank you very much for watching.